Alright, so now I will be explaining another article which is called Neural Shift Reduce CCG Semantic Parsing. CCG stands for Combinatory Categorical Grammar. So we use the shift reduce. There are several ways for semantic parsing, just the sequence-to-sequence model, or the graph-based approach, or the third approach is shift reduce approach. For example, another approach is like semantic things like tagging. People in Zurich University, they use that. And there are many other paradigms. And for example, the unsupervised or semi-supervised approach uses the idea of variational autoencoder, combines it with the supervised approach, so it's a semi-supervised approach. So there are many approaches to handle semantic parsing, but this CCG is invented by great people in Edinburgh University in Scotland. And so this article is from 2016. So if you like this article, I predict that with high probability you will also like these articles as well. So here we are transferring a learned grammar. This is becoming a new fashion because your CKY algorithm, you can do everything with CKY, but it's a little bit noisy. That's why you want to take advantage of this noisy version of parsing, and you transfer it to something that you can then do kind of inductive bias. There are several ways to do inductive bias, but here they are using an interesting approach. They are combining with the power of shift reduce parsing, because shift reduce parsing is really fast. It doesn't need the computational complexity of CKY parsing. If you're using the graph-based algorithm, at the end of the day, you should use CKY, and CKY has cubic computational complexity, so it takes time. So that's why many people like shift-reduce parsing. And even cognitive scientists say that shift-reduce parsing is like how the brain learns. For example, the way my 4-year-old niece learns everything is more closer to shift-reduce parsing. But I don't think my niece uses, her brain uses that graph-based algorithm CKY parse, so it takes time for her to reply. So that's why we like shift-reduce parsing. But here we are using for this combinatorial categorical grammar. I have a playlist for combinatorial categorical grammar that you may be interested in. So let's go to the CCG tree. This is an example. I've explained it several times. But here, if you check part 5 of my playlist on dependency parsing, and also part 6 of that playlist, then you're ready to understand this lecture. So please watch these 2 lectures in my YouTube channel so that you can understand and appreciate this article. So our goal is to learn a function that, given a sentence X, and we map it to its formal representation of meaning, our meaning Z. And we assume we access to a training data set of these meaning representation. For example, for n sentences, we have n meanings. But we apply the abstract meaning representation. This is a kind of formalism, just like lambda calculus, AMR, discourse representation structure. So there are many formalisms to just represent it. You can represent it in SQL if you're working in a relational database, you can represent it with SparkQL if you're working with knowledge databases. So there are many ways. So this CCG tree, for example, we have types. And you have entity, your input, your output is true or false, is Boolean. And we have also complicated types, because each word has a category. As I said, category. When I say category, it means a super tag is syntax. It has syntax, but it also has that lambda expression. So, and in any shift reduce parsing algorithm, you have some actions. So your actions could be just shift, or complex actions like unary and binary. Binary is that you have two CCG here, you have two categories, you combine them. So in order to say what is the probability of a given action, because once you in any shift reduce algorithm, you have a stack and you have buffer. Usually we use just the top of the buffer, and we use the top two of the stack, and top two elements of the stack. So we represent them, and then you say what is the probability of a given action, of one action. So what is the probability of an action if you have configuration? So because we are creating a tree, so these are configurations. Another tree could be like this. So there are many things that are generated. So what we need is what is the probability of action? What is the probability that this is, for example, unary, this binary, it's just shift. And because these are independent, we assume they are independent action for any context. So we multiply them for any configuration. We multiply them because these are independent. We assume they are independent, just like the idea of potential in graphical models. They are independent. We multiply them. I've explained it in different contexts, in conditional random field and in graphical models. So you understand this. But this is just one tree, so you should marginalize over all possible trees. And this way you can say what is the probability of some z. Z is your logical form. And so we should embed the configuration. How do you embed the configuration? There are several ways. You can use, for example, if you like recursive neural net, you can use it, because the problem with recursive neural network is that you should have that graph. But here we have that, and we have that because we are using this article is a little bit complex, because you are using shift reduce paradigm, but at the same time you are using because we are transfer learning, so we are also using the CKY parsing. So we assume that we have the parse, we have something has generated, some graph is generated. So we want to represent this configuration. A good way is that recursive approach. But Christopher Manning has created another approach as well. I mean, he invented many things like glove word embedding, like tree LSTM, which is very similar to recursive neural network. But tree LSTM, that I've explained in a different lecture, tree LSTM can also be used here. But in this article, they used recursive neural network, which is a different approach. And for action embedding, we can use. So let me explain this algorithm. So we assume that we get trees from that CKY parser. So we have for example, we have a third-party algorithm. Somebody gives us this CKY parser, so we have access to these trees. But what we are doing is that we can work on this and calculate the probability minus log probability of this action given configuration that I explained. And in machine learning, we always regularize everything to avoid overfitting. And so we are learning this parameter theta because you have access to the loss, and we backpropagate. So backpropagate the gradient of this, and so we learn the model parameter theta. So as I said, it's noisy. What you have gotten is noisy supervision. The CKY, because it fails to correctly parse 40% of training data, especially here that we are using the CCG, because each word is a complex thing. It's like a tree. And so this is the probability of action given your configuration. And this part comes from what is the f of action, but this part is using that multi-layer perceptron acting those things from stack and buffer and action history. So you see that the blue one, what is the blue one? This is syntax. The syntax is better than the times when it is both syntax and semantics, which is this color. But the worst is this CKY parser. I mean, the text time, the wall time is high, so that we want to learn it. The paradigm of pre-training and those things is getting more and more attractive in these days, especially in 2023. Of course, we are at the beginning of that, but I predict that there are a lot of papers that will come that just use these idea of pre-training. I mean, because the CKY parser takes time, but I've seen an article from Dan Klein, if I'm not wrong, that he uses, they pre-train that, and they attach just a number to each span. So because each span has a score, so they're learning that. So it's a nice research direction. And there are other ideas. So if you like this article, with high probability, you also like this article, and universal semantic parsing. I think I've explained this. Yes, I think she is in Edinburgh. I think I've explained this article. Universal semantic parsing. And